talked about last time was runtime environment, right? So what's the context in which the compiler generates code? What the compiler is doing is figuring out the structure of the input program. That structure indicates what the computation is supposed to do, the actions in the computation. And then that, coupled with the compiler's knowledge of the runtime environment, lets the compiler generate code that the input program structure dictates. So what we did last time was we discussed specific assumptions about the runtime environment. Okay, we talked about the control stack. We talked about the activation record. What happens when, what information needs to be saved. Again, I want to emphasize that what the compiler needs to do is use whatever information it has to generate code such that when that code gets executed at runtime, the original computation is carried out. Okay, now, this is something that a lot of the time, a lot of people have trouble separating. And what people a lot of the time have issues with is thinking that if the input program performs a certain computation, that computation is being performed or being kept track of by the compiler during compilation. Okay, so if I do the analogy with the calculator example that Sam has been discussing, what a calculator does is it reads in an expression and evaluates it. So if you think of evaluating the expression as executing code, executing the expression, then the calculator is not waiting until a later runtime. The calculator says, here's an expression, let me compute the value. That's different from what a compiler does. Okay? There's a lot of similarities between what the calculator is doing and what the compiler is doing as far as the front end is concerned. The calculator, like the compiler, reads in the input. The calculator, like the compiler, parses the input and figures out its structure and perhaps constructs the syntax tree. But then at some point, the two diverge, and the calculator says, I'm going to go ahead and carry out the computation right now. So if the computation is 3 plus 4, the calculator will say, I will carry out the computation. The answer is 7. Here it is. The compiler, on the other hand, will say, OK, the computation is 3 plus 4. I will generate code which, when the programmer gets around to executing it at some later point, that will then carry out the computation. Okay, so there's a delay phase. So now I want to talk about code generation. Usually, compilers break up the process of code generation into two parts: intermediate code generation and final code generation. So far, we've talked about lexical analysis, syntax checking, semantic checking. All of that involves taking the input sequence, breaking it up into tokens, and massaging the tokens. Okay. Then you take this token sequence. The intermediate code generator then maps the token sequence to some different representation, intermediate code. And in fact, there might be more than one different intermediate representations. And that eventually gets taken by the final code generator and gets mapped to final code. So the reason for these multiple steps is that, well, there's a couple of reasons. One is that very often the source code is at a much higher level of abstraction than the final code. So source code will offer abstractions, language level abstractions, that are way more abstract, way more than what the final code offers. So a typical example would be that in C, for example, you have things like structs, and you have function pointers, and you have arrays and records and all kinds of things, right? You have while loops and so on. At the assembly code level, you don't have those things. If I go for a higher level, more abstract language, in a language like Java, you have classes and you have inheritance hierarchies and so on. None of that at the final code level. So one reason for going through intermediate code is that instead of taking a big jump from this high-level abstraction to the low-level concrete language, huge big jump, instead of making that big jump, it's much easier implementation-wise, to make a series of small jumps. So we go from source code through a smaller jump to an intermediate code, and perhaps another smaller jump to another intermediate code, and then a not quite so large jump to final code. So that's one reason that it makes the implementation simpler. Another reason is for portability. If I'm building a compiler that potentially supports more than one source language, more than one front end, and or perhaps more than one backend, so more than one target platform, then by going through an intermediate representation, I cut down hugely on the complexity of writing compilers that can support multiple different front ends and multiple different backends. Okay. So we'll talk about intermediate code generation first. The syntax tree thing that's in your assignment is an example of a kind of intermediate code, and we'll talk about that very quickly. And we'll talk about at least some of the intermediate code generation as being implementable via syntax directed translation, so that we can actually fold it into the parsing process. So what will happen is, at this point, you have grammar rules, and the grammar rules work on tokens, and they give you the structure of the input program. The first step of intermediate code generation will take the token sequence and use semantic rules, syntax directed translation, right? So each grammar rule has some semantic rule associated with it. It'll use semantic rules to get us to syntax trees, which is a high-level intermediate code. Once I have syntax trees, now I have a representation of what the computation is about. Okay, the syntax trees are in a very real sense, a source code language independent representation of what the computation is about. At that point, I can say, you know what, I don't need to deal with YAC parsing rules anymore. I can take my intermediate representation and massage that, and that'll turn out to be hugely convenient. Okay. As you have no doubt noticed, anytime you introduce new stuff inside of your YAC parser, you introduce a semantic action somewhere, potentially things break. You get a shift reduce conflict, you get something else. YY text has the wrong value. Things can be fragile because of assumptions that are built into YAC. So the minute we can get a representation that is no longer reliant, that's no longer married to the YAC representation, things become simpler. So that's another rule we'd prefer to go to, syntax trees. So different kinds of intermediate languages. We have high-level and low-level representations. Okay, high-level languages, representations, as the name would suggest, are closer to the source language, and so they tend to be more machine independent. Because they're closer to the source language, it's easier to generate code for them. It's easier to go from your token sequence or the YAC parsing rules to a high-level representation such as a syntax tree. On the other hand, because it's further away from the target machine, doing optimizations on high-level representations can be harder. Okay. The reason I say can be is that, of course, the details depend on the specific kind of optimization you're trying to do. But a lot of the stuff that compilers do are not as straightforward when you're reasoning at a high level. Low-level representations, these sort of kind of look like machine-independent assembly code. Okay, so there's names, there 3 address code and RTL, and we'll get to those. But for now, take those as machine-independent assembly-like representations. So they're low-level. They seem closer to the actual machine. Machine-independent, more or less, but closer to the machine. That makes it easier to do optimizations. Okay? And if we have time, I can talk about some of that. It makes it easier to do optimizations, and it makes it easier to do final code generation. But because this is lower level, going directly from a source language or token sequence, which is about the same, to a low-level representation is not always straightforward. So the way I'll present the code generation process to you is to go from source representation, token sequence, to high-level representation, syntax tree, and then syntax tree to low-level representation. Okay? So here's the relationship between syntax trees and programs. So conceptually, what a program has, when you write a program, what's going on? A programmer who writes the program talks about two kinds of things. Okay? There are objects that hold data, okay, variables and structures and arrays and so forth. And there are computations that operate on those objects. Okay, so in terms of the program text, a programmer says, here are my data structures, here are my declarations. So the programmer declares stuff, declares the things that will be operated upon. And then the programmer writes code that says, here's how the program will operate on these things. So that's what I have at the program level. I have declarations which talk about those things that contain the information, and I have computations. Well, the computation doesn't actually happen until runtime. So what the program has is an encoding. It's a representation of the computation that will happen at runtime, right? And these encodings, the code, refers to the declarations and says, here's how the computation will operate on these data. What the compiler needs to do is to take these declarations and map them to machine-level entities. So we saw this when we were discussing runtime environments last time. And there was a distinction that I made that at compile time, I have source-level entities which are mapped to locations by environments. And at runtime, locations are mapped to values by the program state. Okay, so the compiler needs to create environments that map these declarations to locations. Okay, so variables get mapped to locations. A local variable gets mapped to a stack slot of some number of enough space to accommodate the type of that variable. A global variable gets mapped to some global memory. And the way the compiler does that is by keeping track of things in its symbol table. For the type checking assignment, you haven't had a need to go and actually allocate locations to your variables. So what you've done is you've said, here's X. You've made a little bit you've kept a little bit of information about the location. And at this point, the little bit is very little. It's where in memory it will lie, in a very crude sort of way. Is it in global memory or local memory? Right? So you've made that distinction in your symbol tables. And you've implicitly noted how much memory you'll need by keeping track of the type. Okay, so there's a little bit of information in the symbol table, but you haven't had to go all concrete quite yet. So that's going to happen as we get closer to the machine. But your compiler is keeping track of declarations in the symbol table. And just as the source program encodes computations that operate on these variables, similarly, in the compiler, there's an internal representation that refers to operations on these things that are in the symbol table. So there's a parallel structure. Okay, there's a parallel structure between what's happening at the program level and the internal structures that the compiler is maintaining. This is not a surprise, because at the end of the day, what the compiler has to do is it has to take these encodings and map them to instructions that carry out the computation that this thing describes. Right? So the compiler has to say, OK, here's in the source program, there's a while loop. So I need to generate code that will carry out the computation of a while loop. OK, here's a switch statement. I need to generate code that will carry out a switch statement. So the compiler has to have inside of it, it has to construct something that resembles what the program does, what the program talks about. So this doesn't come as a surprise. And the stuff that I have in blue is simply making concrete what it is that the compiler does to reflect what the program is stating. So the program the program has an encoding of a computation, And those computations operate on things that are in the declarations. In the compiler's representation, it constructs some encoding of the computation. And for now, that will be the syntax tree. And the syntax tree refers to things that are in the symbol table. Okay, so now let's go and make this more concrete. Each node in a syntax tree represents a computation that's going to be performed. So a syntax tree shows the structure of a program very explicitly. Okay? And what it does is, what a syntax tree is it takes a parse tree and it abstracts away irrelevant detail. There's a lot of detail in a parse tree that comes from the particular grammar. Okay, it comes from a particular grammar. And well, let's do an example. Let's see if I have a marker. Here's one grammar for expressions. Okay, suppose my grammar is for simple expressions. So I can have E plus E or ID. Okay, and this might be a parse tree for a simple expression, ID plus ID. Okay, so this is one simple parse tree. And the input string is ID plus ID, right? So this is the parse tree. Here's a different grammar for the same for the same language. E goes to E plus T, or T goes to T. T goes to ID, let's say. So I've just introduced a little bit of indirection. And from this grammar, the parse tree would look like this. E plus T, E goes to T goes to ID, this T goes to ID. Same input string, ID plus ID, but the parse tree is different. So the parse tree arises out of the grammar that I'm using. And for whatever reason, I might choose to use one grammar or another. You guys took the grammar that you were given initially, and you've made changes to it for good reasons. But as the grammar changed, as you made changes to the grammar, for example, to eliminate an ambiguity or to introduce better error handling or whatever, as you made changes to the grammar, the associated parse trees also change, just like here. But sure, the parse tree may change, but the actual computation underneath isn't changing, right? This, in both cases, the computation is, look, take the two identifiers and add them. And that's what a syntax tree does. A syntax tree captures the actual structure of the computation, and it abstracts away details of the grammar that were important for parsing, but not necessarily important for subsequent code generation. So each node represents a computation. The children of the node represent what that computation is going to be applied to. Here's an example. Okay, so this is a more complex version of my second grammar there. So this allows addition, multiplication, and parentheses. And here's a big old parse tree for ID plus ID times ID. And a lot of this stuff is just straight out of E goes to T, T goes to F, F goes to ID. Well, E goes to T, T goes to F, F goes to ID. But you know, computationally, what is this expression saying? It says multiply these two guys and add the product to ID. So from a computational perspective, I want to say, look, this was all well and good for parsing, but now if I want to talk about code generation, if I want to talk about the actual computation, here's the structure of the computation. Multiply these two guys and take the product and add it to this guy. Right? So this is the syntax tree. Each internal node of the syntax tree represents a computation. Right? Where am I? Each node represents a computation. The children represent what the computation is performed on. Each node represents a computation, a multiplication operation, an addition operation. And the children represent what that computation is performed on. So this multiplication is applied to these two guys. This addition is applied to this guy and the result of this multiplication. Okay? So here's a quickie summary of what, just generalizing that idea and saying, okay, we have different kinds of computations in my language. What do my syntax trees look like? For expressions, your leaves are identifiers of constants or whatever else leaves can be, okay, whatever bottom level base computations you have. And internal labels, internal nodes are operators, and they capture operations. Okay? So the children of a node are its operands, and there's your ID plus ID times ID expression. And you can generalize this to other operators as well. You guys were up late last night.
Yep.
I see people falling asleep. You know, syntax trees get the feelings hurt. So, question for you. Suppose, so let's go with this idea that an internal node represents some computation, and the children of that node represent what that computation is applied to. So suppose I have an array reference, A subscript E. Right? So this is an expression, because I can use this as part of an expression for, say, addition or multiplication or whatever. What should the syntax tree for this look like? There is no unique right answer. I'm curious about your sense based on that idea that internal nodes labeled with operators, the children are the operands, leaves are identified as the constants. What operation am I performing here? What's that, Andrew?
Like an array index lookup.
An array index lookup, okay. All right.
I mean, you're allowed to have an expression as
Come on, let's show me the syntax tree.
because you're allowed to have an expression as the index, so you probably would have some sort of expression node that is child of this has to be an identifier, not non-expression.
Well, that could be an expression too, right? This could be an expression.
It could be part of an expression, but
So
this has to be an identifier. Right?
Not in C minus minus, yes, but let's suppose we're talking about C. So this itself could be an expression, right? X arrow Y bracket something, right? We could have an expression that you could have an expression like that in C. So what should this look like? That's okay. I'm curious to hear what your thoughts are, and I know there are people along there in the classroom who will be happy to help you. So let's work this out. Once we work out the general case, the special case for C minus minus will fall out easily, right? So this is a good investment.
So, but yeah, so if you had some sort of expression node with all of its attendant, operators and identifiers or other expressions.
Mm-hmm.
Or whatever.
Mm-hmm.
Something like this. Another expression. I was just thinking. So something like a node that represents an array lookup that would have a reference to the expression representing the outside identifier and the expression representing the index. Or possibly that could just be another expression node in the operation.
So pick one. Which one do you want?
Or we could generalize it.
Okay.
We have the lookup. I mean, an expression would have an operation inside of it, plus, minus maybe the operation would be lookup. Another expression.
That's pretty good. Thank you. I like that.
Cap.
I have the cap. Thanks. So this is. I was thinking of something very similar. So I'll stay with Andrew's. What I had been thinking of was a lookup, and I was going to write it this way, but same deal. It's exactly an expression lookup. And the children are whatever the tree is for E1 and the tree for E2. Okay, so I have a lookup. Now, if I had the general C situation that I had explained earlier, where this thing could be some complex expression itself, that would be the syntax tree for E1 over here. And this itself can be some other big old expression, and that's the syntax tree over here, right? And the operation itself, as Andrew said, is a lookup. And how you write it doesn't matter, the equivalent, right? So good, thank you. We can lift that concept that internal nodes represent what the computation is, and its children represent what the computation is performed on. That really is the intuition over here. We can lift that and apply that to statements as well. Okay, so a while loop has two components. One is the condition that is tested for the while, and the other is the body. So here's the syntax tree for the body. Here's the syntax tree for the expression. And there's a node that says, this is what the tree is. This is what the tree node is. Similarly for ifs and assignments and all of the others. Okay. So you can see that a few sort of fairly obvious comments. The type of a node tells you what the computation is. Its children tell you what the computation is performed on. The type of the node tells you how many children that node has. So some have 2 children. These guys have 2 children. And if has 3 children. I'm trying to think of any that have more than 3. A switch has arbitrarily many. That's an interesting one. I don't like I don't like programming up things that have an arbitrary number of children. So it's an interesting question of how one would program that up, a switch. Similarly, a function call can have an arbitrary number of arguments, right? Now, a function call can have an arbitrary number of arguments. So let's just take a look at that for a second. The way I might do a function call in the syntax tree is to say, look, here's a call. The type of computation is a call. And what is this type of computation applied to? Well, here's the function. In C minus minus, this has to be an identifier. But again, in C, because you have function pointers and such, it doesn't have to be, right? So in principle, this could be a syntax tree itself. But nevertheless, at the end of the day, this is the function that is called the callee. And so I have a couple of options. One is to make this open-ended and say, I can have as many arguments as I want. Programming that up is kind of tricky because it's hard to write structs that have an arbitrary number of children, of fields. So a straightforward way to do that is to say, there is a child, which is the argument list. Okay, and this is a dynamic structure that can be arbitrarily long. Okay, so now one could imagine applying a structure like this for switches as well. So I could imagine having a switch. There's one child, which is the expression that I switch on. And then there's another child, which is a list of labels and code. Okay, so each of these is label plus code. A label is a constant. The code is a syntax tree, right? So you could imagine making it work like that. You don't have switches in C++, but you do have function calls. So you'll want some way to implement them. Yeah, Brian.
I'm having trouble figuring out exactly how you're supposed to handle like what's in the symbol table and what's in the syntax tree. The symbol table is created from the parse tree.
So the question is, what is the relationship between the symbol table and the syntax tree? Where am I on time? Let's quickly talk about that. Then I want to take a quick break, and then I want to come back and actually talk about generation, code generation. So let's go back to our trusty ID plus ID times ID. Okay, so ID plus ID times ID. Actually, let's go ahead and do an example. F int x sorry, let's try this example. Int a, int f, returns x plus a. Okay? So I have a local, I have a global, I have a function, I have a statement. So here's what my symbol table might look like. So the local symbol table and the global symbol table. There's an entry for A, and there's type and scope information and so on, and I'm omitting that for now. And the local symbol table has X in it. And you understand that there's really a lot more complicated structure there. There's a hash table or a linked list or something, and this is a pointer to a string. We're skipping all that, right? You can figure out those details. So here's a global symbol table entry for big A, local entry for X. So I come over here. The expression tree for this looks like I have a plus node. What are the children of the plus node? Well, this is an addition operation that's applied to the variable x and the variable a. So I'm going to go back and show you a picture from a minute ago. So just as in the program text refers to declarations, here my syntax tree will refer to the things that I am computing on. So this thing will be a pointer to here, and this guy will be it's x plus a. So this is a pointer to here. Okay, and then my return will itself be a syntax tree node, and that's the expression that's associated with it. So return statement that doesn't have an expression would have a null for that field. Okay? So this is the syntax tree that I would construct for the body of this simple function. And then in the C++ compilation model that we've been talking about so far, we're compiling a function at a time. So having constructed this tree, I would throw it away. And I would go and compile the next function. And I would construct a syntax tree for its body, and then I would throw it away. Next assignment, what would happen is we'd construct this tree, and then we would traverse this tree, generate MIPS assembly code, and then throw it away. Okay? So now you had a question.
No, Mike, you sort of answered it. I was thinking, okay, so now we actually have to build them both like simultaneously and deconstruct them simultaneously. And when you run leave the scope of both, then you destroy that as well. You destroy all this stuff in the syntax tree onto that function.
That's right. So when I leave the scope, when I leave here, when I leave this local scope, I need to deallocate the local symbol table. I need to, because otherwise when I go to compile the next function, I could mess things up. So the local symbol table needs to get freed up. At the same time, I free up the local syntax, not the local syntax, the syntax tree for the body as well. So clearly, before I free up the syntax tree for the body and the local symbol table, I need to generate code for the body, right? And right now, all we're doing is we're constructing this intermediate representation. We aren't writing it out, but what we will do the next code generation assignment is, having constructed the syntax tree, at this point, or maybe at this point, we'll say, okay, now I have seen the entire body of the function. I've constructed the syntax tree. Let's traverse it, generate code, write that out to a file. Then I'm done with that function. So now I can get rid of all of the, I can throw out the local symbol table, and I can throw out the syntax tree. Okay? Let's take a quick break. We'll come back and talk about generating code.